Morning students, we are going to discuss about the diode current equation. Today, the diode current equation already we have obtained from this quantitative theory of your PN diode currents. So the quantitative theory of PN diode currents, we have obtained a current equation which relates the voltage and current of the PN diode. So this diode current equation only we are going to discuss today. So the diode current equation is obtained by the relation I is equal to I naught e power V by eta Vt minus 1. So what is I naught? I naught is the reverse saturation current which will be expressed in microamperes, and V is the applied voltage or the external voltage. Eta is the constant which is 1 for germanium and 2 for the silicon. And what is Vt? Vt stands for the volt equivalent temperature. So Kt by Q, where K is the Boltzmann constant 1.38 into 10 power minus 23, and Q is the charge of the electron 1.602 into 10 power minus 19 coulombs. Now we are going to obtain the expression for this Vt in terms of temperature alone by substituting the Boltzmann constant and the charge of an electron. So Vt is equal to Kt by Q, so which can be written as T by Q by K. So what is the value of Q? Value of Q is 1.602 into 10 power minus 19 divided by 1.38 into 10 power minus 23. Okay, so you will be getting that value should be approximately 11,604. We are giving that value as 11,600. So that is the direct formula you can apply. Where T is the temperature of the PN junction diode, which is expressed in Kelvin. So T can be expressed in Kelvin means some degree centigrade plus to convert that it will be 273 added with 273. So what it represents in terms of Kelvin. Okay. So this, if the room temperature is 27 degrees centigrade, the temperature will be taken as 300 Kelvin. So for room temperature is nothing but 27 degree centigrade. It will be given as 300 Kelvin. Okay. Then we are going to explain the same equation for this in terms of your germanium and silicon. So you are giving the value of germanium and silicon over here. So at the room temperature, if this Vt is equal to 300 divided by 11,600, it is approximately equal to 26 millivolts. Okay, so you're going to apply this for your room temperature. So for this room temperature, what is your value? I is equal to I naught e power. So generally is I equal to I naught into e power V by eta Vt. So V we don't know and eta we know. What is the value of Vt for room temperature? It is 26 millivolts minus 1. Now 1 by 26 millivolts, this value is approximately equal to 40. So I is not e power eta I naught e power V 40V by eta minus 1. Now give for germanium, your eta is 1, so it becomes I equal to I naught e power 40V minus 1. And for silicon, the eta value is 2, so 40 divided by 2 becomes e power 20V minus 1. We have obtained this value. Now, in a forward bias condition, we will be keeping on increasing the voltage. The forward bias condition will be increasing the voltage means e power 40 into V is a higher value means this should be this minus 1 can be ignored here. the -1 can be ignored if the V applied voltage is very, very greater than 1. Okay. If the same current equation when applied for reverse bias condition, instead of this the same equation, here you will be using a minus to represent this reverse bias condition. If this reverse bias condition, if you are increasing the voltage now, the forward bias condition while increasing the voltage, e power infinity becomes dominant. So -1, that one value we have neglected. If you are increasing the voltage in the reverse bias condition, if our minus term becomes very, very less than 1, so this term can be negligible. Therefore, I is equal to minus I naught. So the forward current, we can conclude that the forward current is opposite to the reverse saturation current. So the diode current equation, which relates the current equation, and we have analyzed in terms of the type of material applied and voltage when it is higher, and second, when applying the reverse bias condition, the current is equal to opposite to the reverse saturation current. Okay, thank you, students.